Nuclear fission is the idea that you can take an atom and split it apart into multiple different smaller size atoms. Now, the way that we do this is we use neutrons and we shoot it at the nucleus of a highly unstable atom such as uranium-235. When we do that, it becomes uranium-236, and it holds that state for a few fractions of a second, maybe a second at most, and then it splits. The reason why it splits is because as U-236, it is too unstable. And since it is too unstable, it will split into smaller size atoms, as well as, if you pay close attention, produce a few extra neutrons that shoot outwards. In the process, there is a significant release in energy. The reason why there's a release in energy is it turns out that the two smaller nuclei that you saw go to the right and left of the screen actually had slightly less mass, along with the 3 neutrons. All of those 5 things combined, the 2 nuclei, the 3 neutrons, have slightly less mass than this uranium-235. And the loss in mass is released in the form of energy. E equals mc squared. Now, for a chain reaction, which is what we do in nuclear power plants and nuclear bombs, is we have a whole bunch of uranium-235. And I'm going to target this one right here. And when I shoot it, just shooting 1 neutron, this will cause the uranium-235 to become uranium-236. And it will split into 2 smaller atoms as well as eject 3 neutrons. Those additional 3 neutrons are going to go hit other uranium-235s, turn them into 236, and boom. Now, where's uranium-235 found? It's found right below your feet in the earth. You'll notice that a nuclear reaction or a nuclear detonation is not a natural disaster like a hurricane or a tornado. We never see that spontaneously some uranium-235 in the Nevada desert went ahead and detonated, killing millions of people. The reason is because uranium-235 is naturally embedded in uranium-238, which is stable. So when that uranium-238 surrounding the uranium-235, what it will do is it will absorb the extra neutrons, or it will just allow them to pass by. Thus, we don't get a chain reaction. You may have heard of a term called enrichment, and the idea is this. This is kind of how we're going to find uranium-235 naturally. It's going to be a very small quantity surrounded by uranium-238. So what we do is, I am dramatically simplifying the process, but what we do is we chip away at the uranium-238 and we add in some uranium-235. This process is called enriching. And basically we're using centrifuges to do this because uranium-235 is less massive than uranium-238, and therefore in a centrifuge the two would separate. It is a very difficult process to do. Now, we can do different levels of enrichment. So example, in this one here, my reaction kind of fizzled out pretty fast. This would be something that will be a little bit more appropriate for, say, a nuclear reactor. Don't pay attention to these numbers. That's not quite relevant for this. So the idea, though, is I would do that on a nuclear reactor, and you notice how the reactions have all stopped, which is good. I release some energy, and I can then convert that energy into electrical energy to use as electrical power. Now, let's say I want to go ahead and obliterate my enemies. So I go ahead and get some highly enriched uranium, which is a significant amount of uranium-235. There will still be some 238 left around. And then I have a triggering mechanism, and boom, when one goes, it causes a chain reaction and blows everything else away. So you'll notice that the uranium-238 has turned into uranium-239. Uranium-239 is relatively stable, especially compared to uranium-235. It is radioactive, and it will turn into neptunium, and that neptunium will eventually turn into plutonium, and then we can use plutonium, just like I used the uranium-235, to do more fission reactions, and in fact, those fission reactions would be even more energetic. So that's the concepts behind what's happening. Let's take a look at some of the problem solving that you'll be doing. If you are confident in how to set up these equations, you can go ahead and kind of stop here. Before you do, one other thing I want you to point out, because the other example I'm going to show in here is an E equals mc squared example with this problem here. But I'm going to start off by showing what this uranium-235 reaction would look like. So what happens is the uranium-235 nucleus absorbs a neutron and fissions. One product is 134 CS, and 2 neutrons are released. What is the other fission product? Answer in terms of AZX. So what I have is 23592 uranium plus 10 a neutron, lowercase n. That's going to yield 13555 CS plus 2 10 neutrons. I can put the neutron in parentheses. 2 neutrons are released. And then, well, what's left over? I need to get 236 in my count on the top for mass. So I got 134. This takes me to 136, so we'll go 100. And then 92 and 0 is 92. So 55 plus 0 plus what would be 92. So 92 minus 55 would be 37. And I'm looking for the 37th element. So let's go to the periodic table. Of course, I don't have it up. 37th element is right here, rubidium Rb. So we'll come back. We'll type in Rb. All right, let's take a look and make sure that that works in web design. 137 Rb. Caret 100 underscore 37 Rb. And I actually typed it in the wrong question. We want it up here in question 1. Okay, submit. And there it is, green check. This was for a different problem. I typed in the wrong spot. So the next thing, though, I want to talk about is E equals mc squared. Question is, well, how much energy gets released? This is where Einstein's idea that mass and energy are actually the same thing, and the linkage between them is the speed of light squared. So in one fission reaction, we have a loss of 1.067 E negative 27 kilograms. How much energy is produced in one? So that would be the energy produced is 1.067 E negative 29. C is 3E8. That is the speed of light. That is a constant. It will always be 3E8 squared, or 9E16 if you want to shorten that. All right, so I punch into my calculator, and the result is 9.603 E negative 13 joules. That seems like a very small amount of energy, but remember, that's only one fission reaction. So the second video that I'm going to have, which I'm calling optional, kind of walks you through the last question on the WebAssign. In this case, we're still using that same mass that we just used, but now we're going to do it for an entire 50 grams. 50 grams, to give you an idea, is about the mass of an egg. And 50 grams of uranium will produce 1.27 times 10 to the 23rd reactions. So the second video that I'm going to do shows you, well, what does that math look like and how would it power your house?